Hello and welcome, Lars. I'd like to thank you a lot for the great opportunity to hear you do a talk about science and science, language, data, fair ontologies, and knowledge graphs. So everything we talked about last week with Annalena, you will go into much more detail. We talk about it in essence next week in like 10 to 15 minutes.
Sounds good.
All right. Thanks for this. The stage is yours.
Okay, this is a introductory talk to ontologies and knowledge graphs, and also a bit fair of data and metadata, and it take about an hour, and it tries to basically start with how humans communicate and then see how we can transfer that to the problem of how humans could communicate with machines and machines with machines. So let's first take a look at how we communicate terms. So when we exchange information, we usually do that with the help of language, of course, which means terms and statements. And the recipient of a message must be able to read, understand, and correctly apply these terms themselves and the statements. And that's basically requires that information must have certain properties of being readable, interpretable, and actionable. And maybe you've heard that also for machines, that data and metadata should be readable, interpretable, and machine actionable. So we take a look on here first what it needs so that terms are human readable. So I would define as something being human readable as a sequence of symbols that can be assigned to sounds. So if you look here, this is something that I'm capable of reading. This not because I don't know the symbols. I cannot attach any sound to these symbols, so I cannot read out loud this, whatever that means. For others, because these are Arabic characters, others could read them, of course, I can't. Now, if we look at interpretable, then we can say that a sequence of symbols that are readable, so we refer to the definition earlier one, and that can be assigned a certain meaning. So something that I can read out loud and make sounds, and then also assign a certain meaning to that sound. And see here, we have the term tree. I can read it and I know what it means. It's interpretable. This I could read, but it has no meaning. Then the third term, actionable, that's a sequence of symbols that are interpretable and that can be formed into a meaningful statement with other sequences of symbols. So here we have a couple of sequences of symbols that refer to terms, and I can read them all, and I can make a statement with them using one of these terms, and then I can show that the term is actionable. I know how to use it, how to apply it. The fir tree is a tree. And this goes back to a more fundamental problem that we have when we communicate, and that's world building in a way. So we take here the position of scientific realism, that we assume that there are real entities, which means objects, processes, qualities, and states that exist independent of me looking at them, perceiving them. So they are mind independent. And then through the process of perception, we build cognitive representations of these real entities. So when I look at a tree, I don't have a tree in my mind, of course, but I have a cognitive representation of that tree. So cognitive representations are thoughts, perceptions, conceptions, ideas, beliefs about real entities. And now if I want to communicate about them, I can use two different ways. One is I use something that resembles the real entity, like for instance, an image, an audio recording, a video recording. And I could show that to someone else and then communicate about that. So that's part of the communication then. iconic representational artifacts. And they take important roles in communication. So whenever we need independent evidence to convince someone of the validity of a statement, I often have to refer to, for instance, photographs. And also when I want to communicate things that are very complex in terms of their spatio-temporal relationships, it's much easier to show an image than to talk about it. So for instance, a family tree, I could communicate a family tree much easier by showing the tree instead of talking about it. Now, the other way to communicate is, of course, via terms and statements. And the basis here is convention. So there we have agreed upon that we have a certain list of symbols, the alphabet, and we assign sounds to them, and then to certain sound combinations, we assign certain meanings. That's all by convention. So it's not resemblance like with the images where we have the content basically automatically transported through the resemblance. Here we have to do that by convention. And these are then called textual representational artifacts. So words, symbols, texts in general. And these are required whenever we want to make logical conclusions like deduction, induction, abduction work only on the basis of text. But also we often use them when we do rule-based operations where we need some data input. And data in general, at least empirical data, is always textual. It's always textual representational artifacts. So textual in the broad sense, including also numbers and symbols. So when we look at the communication of terms between two humans, the goal is to create the same cognitive representation in the receiver of the message as the sender has. And this works only if both use the same set or a very similar set of conventions. And then we can use text or terms, textual representational artifacts to do the communication. So it's clear that this process presupposes a certain level of knowledge on both sides. Otherwise, it wouldn't work. So two types of information are essential for that to work. And the first is that the sender and the receiver must know what a tree is if we talk about tree. So here is an example of a definition of what tree could mean. It's from Wikipedia, so it's more technical. A tree is a perennial and woody seed plant that has a dominant shoot axis that increases in girth through secondary thickness growth. That's probably not what you usually think about when you hear the term tree, but it is one definition of the term tree and provides meaning to that term. So it's an ontological definition or characterization, and it provides an answer to the question, what is it? What is a tree? It provides knowledge about the meaning of the term, and with that, it provides you with inferential lexical competence, which you need. We need competences if we talk with each other. And the other type of competence we need is concerned with diagnostic knowledge. So when a sender and a receiver they both must know how to recognize a tree. In science, we call that diagnostic knowledge, and it's often tied with methods. So for instance, if I have a certain mixture of substances and I want to know whether iron is part in there as one component, I have certain methods as a chemist to test for iron. It's a method-dependent recognition criterion. So we need these method-dependent recognition criteria, and they provide us answers to the question, how does it look, or how to recognize or identify a tree. And the reference is often made to an exemplar. So we see that we have these scientific collections. They serve exactly that purpose. So if I found a new species, I would collect it and would then make it available in a scientific collection in a natural history museum, and then link a term to that exemplar. But we also, and then I can point to, whenever someone asks, how does that look? I can point to that exemplar. Or I could use other iconic representational artifacts like photos and drawings. And it provides knowledge about the referent of a term, and that's why it's also called referential lexical competence. We have two use cases for this knowledge, this referential lexical competence. So the first is we have the object is given, and then we want to find the matching term. That's the process is then called designation. Or we have the term and we want to identify the object, the matching object. That's then recognizing something. So that's something that we do on a daily basis all the time. And this is also part of the knowledge that you need to make a term actionable for you. If you know how to designate and how to recognize, then you can use the term, it's actionable for you. And this also refers to something that you might have heard the semiotic triangle, where we have the object, which is the real entity. We have the representation or reference, which are the cognitive representational artifacts. And then we have a sign or symbol, which in this case would be a textual representational artifact. So there is some connection here. And you see here the relations go in both directions, and that's basically what we also need and have to think about whenever we want to communicate information, as these relationships must be taken into account, independent of whether a human wants to communicate with a human or with a machine or machines with machines. We have to take care of exactly these relationships. So a summary of that part would be, we have a term, and if we want to communicate that term, we need to know what's the meaning of that term. We need an ontological definition. We also have to know how to recognize the real object that refers to that term or to which the term refers. These are the recognition criteria that give us the reference of the term. And together, this information provides us with lexical competence that we need to communicate the term, in this case, tree. But information, and alongside with it, meaning is not communicated via single terms. So an individual term doesn't provide meaning by itself. It's basically a shortcut for a statement that provides the meaning. So meaning is always communicated via statements, either directly or indirectly by terms to which we have these meaningful statements linked through definition. So let's take a look at how we communicate statements. So statements have a structure, and the structure takes the form of a tree, and it's called a syntax tree. We see here the statement, I am a syntax tree, and you see the different phrases and positions in that tree taken by terms. And the cognitive representation of the meaning, or you could also say the semantic content of a statement, takes the form of a syntax tree. So when you listen to someone, you wait for certain positions to be filled in your tree that you built up in your mind, which is then your cognitive representation of that statement. And as such, it's probably the oldest knowledge graph that we use, although we mostly use it unconsciously. So when we read or hear sentences, we build such syntax trees that go with the statements. And we see when we want to communicate a statement, we also need these conventions. And we have to share the same conventions, sender and receiver, so that the cognitive representation of the statement would be created in the mind of the perceiver. And these rules and conventions are basically syntax and grammar. And they take the function to structure and to provide the structure that is needed to be able to translate a syntax tree into a linear sequence of words and back again. Because when we write, we use a linear sequence of letters, either from left to right or right to left or up and down and so on, but it's always a linear sequence. And also when we talk, we use time and make sounds, and time provides us with a linear sequence, linear order. So we need to, and we cannot communicate a tree in a linear order. So we need additional rules, conventions that help us to translate the tree in a linear sequence and back again. And each position in the tree, and with it, each position in the syntax of a sentence, has a certain semantic role associated with it. And what that means, I can show you with an example. So we have here the statement, Peter travels on February 25th, 2022 with a bus from Berlin to Paris. And here I translated it with the positions in blue of subject and objects, and then in red, the verb or predicate. And I use certain labels here, which are basically thematic labels that give you an idea of what the semantic role of that position is. So here we have a person who is traveling on a certain date and so on. So different positions have different semantic roles, we see. And the positions contribute significantly to the meaning of the statement. And that becomes clear if we take the same set of terms and just change the order, like here. So I changed Berlin and Paris. And the meaning of the statement has changed. So now Peter's not traveling from Berlin to Paris, but from Paris to Berlin, although it's the same collection of terms. So the position of a term in a sentence is important for the meaning of the statement. So what does that mean for the readability of statements and the interpretability and actionability? So readable, a statement is readable. It's a sequence of symbols that can be assigned to terms and sounds with rules indicating the end of terms and statements. So we have here a space that indicates this term has terminated here and a new term is starting. And we have the point here that indicates that's the end of the statement. Here we have no such special characters, so I cannot read it as a statement. Although I could read the different symbols, I cannot read it as a statement. Because I don't know where does a term start, the next, and end, where does the next start, where does a sentence end, and the next starts, and so on. So interpretable, I would define as a sequence of terms that is readable and that based on conventions, so rules, can be assigned to a syntax tree with positions and semantic roles, and thus to a particular meaning of the statement. And this is interpretable because I understand each term and I understand the positions of the terms, and I can then build the syntax tree in my mind when I read that. This is not readable, is not interpretable to me, because I cannot assign any meanings to these words. So also no semantic roles in a syntax tree. I even don't know where the verb is of that statement here. Actionable would be a sequence of terms that can be interpreted as a statement and that can be formed together with other statements into a meaningful narrative. So here I have a statement, I have another statement, and they link to each other, building a meaningful narrative. A fir tree is a tree, it is evergreen and deep-rooted. So the summary here would be, we have syntax trees. Syntax trees provide a structure with positions, designated positions. Each position has its associated semantic role, and together they provide meaning to a statement. And this knowledge about the syntax tree, the positions with the semantic roles, is a requirement for being able to communicate statements. So let's take a look at what data is. And here I provide a definition that is not basically a general definition. It's just for the purpose of this presentation. So data are statements that have been structured in such a way that they can be easily compared and also easily be read by machines. So compared also for humans. For instance, Excel sheets. And here we have an example of a weight measurement of an airplane. And we see here we also have an iconic representational artifact. We have the textual representational artifact of the same object. So we have here a nose wheel represented in two different ways. Then we have the measured quality, which is weight. We have a measurement value, and we have a unit specification. Now, how does a human read that and how a machine? Well, we've learned to read these tables as humans through school and so on. So we learned the conventions, and we can basically, we look for the terms, and then we think about what syntax tree could we use with positions that match these terms to have a meaningful statement. Like here we have object has quality of value and unit. That's my syntax tree with the positions and the semantic roles, and now I can map them, nose wheel, and so on. And basically the same we do for machines. So for instance, we can have tabular data schemata where we assign certain semantic roles to columns and rows. Then we use certain terms for basically providing the information. So data schema are to machines what syntax trees are to humans. They're structures that basically carry meaning. Both define positions with semantic roles. And then we can map that. So we have, in both cases, positions and semantic roles. Now, if we look at the communication and the use of data, it becomes more and more important that we can do that with machines, and machines can do that with machines. Why? Because we are dealing with ever-increasing amounts of data. And data is produced in exponential rates so that we cannot sift through and take a look at them ourselves anymore. We need the help of machines. So we have to take a look at this communication between machines and between humans and machines. So let's have a look at these terms that we talked about for statements and for terms, the readability, the interpretability, and the actionability. What does that mean to machines? Now, we have talked about that, as I said. What does readability of term and statement mean for a human? Now we have to transfer that to machines. And here I quote a definition that is from a white paper of EOSC, European Open Science Cloud group. And they define machine readability as such. Machine readable are those elements in bit sequences that are clearly defined by structural specifications. So what does that mean actually? Well, in the context of knowledge graphs and ontologies, it's about identifying elements. And here, URIs and RDF are important. And as I said, it's in the context of knowledge graphs and ontologies. In other contexts, there might be other concepts that are relevant. for machine readability. So what is a URI? A URI is defined a uniform resource identifier, is an identifier and consists of a sequence of characters used to identify an abstract or physical resource. And we see here various examples. So even a telephone number is a URI, according to that definition. We see here we can identify substructures within a URI, which is a bit confusing because these are also are understood to be subtypes of a URI. But we see here at the beginning, we have the method that defines basically how you can access that resource. Then we have the location part. Where is it located? This is then the URL, and we know that from the World Wide Web. And then we have the name part. That's the URN. And then maybe you have heard also about IRIs, and these are basically URIs which use an extended character set so that you can also use international characters and you're not restricted to the use of ASCII. So for a machine to be able to read a resource, it must be able to identify this string as a resource. And that's the URI for. Now, how are then statements readable? This is where the resource description framework comes in. So the resource description framework, or just short RDF, is a World Wide Web consortium standard, and it was originally developed as a metadata model. But today it is typically used as a general method for describing and communicating graph data, especially in the internet. And core to RDF is the so-called triple syntax, where we have three elements: a subject, a predicate, and an object that form basically a statement. So we have three positions here: a subject position, a predicate position, and an object position. And the subject is always a URI, the predicate is always a URI, and depending on the type of predicate, we distinguish URIs or literals as objects. And here's an example that's taken from the Wikipedia page for George Washington. And we have here two URIs and a literal forming a triple. And as a human reader, you could read that taking a look at the name part here. The Wikipedia page for George Washington has the title George Washington. So that's easy. We have another example of a statement where we have the Wikipedia page for George Washington has publisher Wikipedia. But if we take a look at how Wikidata does that, we see that we not always get something that is human readable out of a URI. So here we have in subject position something that carries no meaning to me, only to a machine. And we also see that in the third position, we don't have a literal here, we have a URI. But we can still translate that because you can make statements where you basically assign a label to this URI using, again, a triple, where in the third position you would have a literal that basically defines the label of that. So here we can then translate that as George Washington is a human being. We have another statement that says also from Wikidata, human is subclass of mammal. And interesting here is we have the same URI in two statements. In one statement, it's in the object position. In the other one, it's in the subject position. And this can then be translated into a graph where we have this resource in one triple in this object position, in another in the subject position. And this resource then basically links these two statements to form a semantic graph. So that's basically the same statement as we've seen before. Here I just used the we come to that, basically conventional labels for these predicates here. So we see for the readability, machine readability of terms, we need URIs, and for statements, we need RDF. And this is, as I said, in the context of ontologies and knowledge graphs. So let's have a look at what machine interpretability could mean then. So we talked about what it means for terms and statements for humans, and we want to transfer that now to machines. And I continue referring to the definitions from this white paper here. So machine interpretable are those elements that are machine readable and can be related with semantic artifacts in a given context and therefore have a defined purpose. Okay, what does that mean? Well, in the context, again, of ontologies and knowledge graphs, it means we have to associate elements with defined and registered terms and align them with positions in defined patterns to add meaning. So let's take a look at. So we need ontologies and we need graph patterns here for this purpose. So ontologies. The web ontology language, also called OWL, is a family of knowledge representation languages for documenting ontologies. And ontologies can be understood to be a formal method of describing taxonomies, which means class, subclass hierarchies of terms, and of networks that essentially define the structure of knowledge for different domains. So an ontology is a taxonomy of terms that then have relations across from one term to the other. And with that, I can then basically describe the knowledge of a certain domain. And three types of resources are distinguished. And here I'm not using URIs because humans don't want to look at URIs. But behind that, it's basically a certain category of URIs. Those that refer to individuals, also called instances, those that refer to classes, and those that refer to properties or relations. So these are technical terms, and we can translate that into our human language. So we need proper names. We need general terms or kind terms, and we need verbs or predicates. And these different resources basically take exactly this function. And then we can build statements, and we can distinguish three types of statements: lexical, assertional, and universal statements. So what is that? Lexical statements are basically technical statements when we want to talk about terms as terms. So I want to talk about the term tree, that it consists of 4 characters, for instance, who first used the term, and so on. So that's statements about linguistic items such as terms, or annotations of resources for instances, for classes, and for properties in an ontology. These annotations are lexical statements then, or provenance metadata for ontology terms, like who created it, from which ontology have I imported this term into my ontology, and things like that. Then we have assertional statements, which are basically statements that are true for a particular known instance, a named individual. Or universal statements that are true for all instances of a particular class. And now we can make, knowing that and having that background knowledge, we can now make a meaningful distinction between ontologies and knowledge graphs. So often these are mixed up, but I think it makes sense to make that distinction. So ontologies usually document knowledge about classes and properties in the form of universal statements and lexical statements. That's the knowledge contained in ontologies, usually. Then knowledge graphs include all this, the knowledge that is in ontologies, but in addition to that, they also have knowledge about instances in the form of assertional statements. So here we have a universal statement that would be part of an ontological definition. We could put that into an ontology. It provides meaning. So let's have a look at an ontology. And I said OWL is basically the language that is used to document ontologies, describe ontologies, but nobody wants to look at that, like nobody wants to look at machine code. So we have basically visualization and editing tools that can be used. And here you see a screenshot of a part of the interface of Protégé, which is such a tool. And you see here to the left the taxonomy of general terms, class terms, and the term count has been selected here. Then to the right top, you see all the lexical statements that for this term count, for the class count. So the label, the human readable label, which is also shown here so that we as humans can read it. We have the definition, human readable, some elucidation, the term editor, and there might be some more. And then down here we have the universal statement for count. And this is basically information that is necessarily true for each instance of count. And it's using specific formalism. Here, Manchester syntax it's called. And it translates basically to every instance of count is also an instance of the class data type. And it is an instance of a class that is defined as being an output of some process counting. So everything that is an item unit and that is the output of a count, where you count something, is an instance of count. That's what it means, basically. So here we have an example of an assertional statement. We have here an individual that is an instance of the class count, which is taken from exactly this ontology, the information artifact ontology, IAO. And it has a value 4. Now, not every count has the value 4. When I count, I not always end up by 4. So the value 4 is only true for this count X. I cannot generalize it. So this statement cannot be part of an ontology where I define the class count and all its instances. So it could be part of a knowledge graph, but not of an ontology, this statement here. Now, what advantages do ontologies bring as opposed to natural language terms? So first of all, we don't have to talk about that. It's machine readable, interpretable, and so on. But it also solves the problem of homonymy. So different ontology terms can share the same label and can nevertheless be distinguished as different resources by machines due to their different URIs. So it could be that I use Washington, the term Washington, to refer to George Washington, to Mount Washington, to Washington, D.C. A machine wouldn't care because I would still have 3 different URIs that refer to these different entities, although each of them would have as a label assigned to it Washington, which of course we wouldn't do that, but it would be possible for a machine to still distinguish them. And also for us, if we take a look at the URIs. But there's many problems still there that we have to take care of. So for the one problem is the problem of terminological interoperability. Interoperability, sorry. So different ontologies can contain terms that share the same referent and the same meaning. So they are quasi-synonym resources. And that's, of course, problematic. And here I use the ontology lookup service and search for the term pressure. And we see I have several hits, all from different ontologies. You see that here in the yellow, the identifier. So different ontologies all have the same resource, not the same resource, but the same term defined, pressure. So how do I deal with that? To machine, these resources are different because each one of them has a different URI. So how does a machine know that we're talking basically about the same thing? If I use pressure from Pato and you use pressure from NCIT, for instance. So the solution is we have to explicitly state that these are synonyms. And this is then called a term mapping. So I have to map my term, in this case, pressure from Pato, onto pressure from other ontologies. And we see here this has been done. So the Pato pressure term is mapped to all these ontologies here. But it has to be done, of course. And then the machine can basically track all these mapping statements and then can make equivalences between them or understand them as synonyms. Another problem is that what I call ontological interoperability. So different ontologies can define terms that share the same referent but have different meanings. And we know that also from natural language. So we have the term morning star and evening star, and it took a long time before humans realized that they share the same referent, which is the planet Venus. So if you take a look into the literature, you see there are different associations with morning star and evening star. These two terms have not the same meaning, although they have de facto the same referent. And also, if you read here Clark Kent and Superman, it's the same referent, but you have different associations with these terms, so they carry different meanings. And we have the same also in ontologies. And here is an example of virus and viruses. So we would think it's the same referent, but there are different meanings linked to them. So you see here, virus is a subclass of acellular structure, which means acellular is not cellular. That's what acellular means. So a virus is a structure that is not consisting of cells. Here it says a virus is a specific type of organism. Organism is usually defined as something that consists of cells. So you see here different meanings. You cannot basically translate one into the other without changing the meaning. So these two terms are incompatible because they use incompatible assumptions. So in this case, we cannot solve the problem of ontological interoperability. So let's have a look at statements and interpretability of statements. And here we need graph patterns. So what's a graph pattern? It's also called a shape or a semantic schema, and there are probably also other terms used for that. They basically take the role of syntax trees, like we've seen them in natural language. They define positions in the graph to which certain semantic roles are assigned. If the same pattern is used for the same type of statement, then statements of that type can be interpreted by machines in a certain way. And then they are also interoperable. And such graph patterns can be formally defined and then used also for validating data using certain languages, like, for instance, Shekel. And here's an example. So here we have the human readable statement, object X has a weight of 5 kilograms. And we have a certain pattern here where we have positions that take certain roles. So here we have the position of an object, here that of a quality, in this case weight. We have that of the unit and the measured value. And we can map them to our statement, human readable statement, with the same positions and associated semantic roles. So it's basically the same. It serves the same purpose, basically, just for machines here in a graph-based environment. Now the problem is here, and I call the problem of schematic interoperability. Different communities may have established different graph patterns for the same type of statement. So here you see the same type of statement in a different graph pattern. We have the same positions identified, the same semantic roles, but in different positions identified in a completely different pattern. And that's because this here is based on the OBO Foundry model. OBO stands for Open Biomedical Ontologies. It's a consortium of people that define certain criteria, and the OBO Foundry basically allows you to then submit ontologies, and they're checked, and if they comply with these criteria, then they are part of the OBO Foundry. And then there is a model that is based on the OBOE ontology that is often used by ecologists. This is used by life scientists in general. And the solution here is, for the schematic interoperability problem, is we have to align the graphs to identify the positions that share the same semantic roles. And then in case different terms are used, so here it's fine because we use in both cases material entity from the basic formal ontology. If it would be from a different ontology, we would have to do the mapping as well. And this is then a schema crosswalk that we can do. So we see, for the interpretability of statements, of terms and statements in the context of ontologies and knowledge graphs, we need ontologies for the terms and graph patterns for the statements. So the last point is the actionability, machine actionability. So we go back against, first short look. Remember how this has been defined for humans, for terms and statements. And now we have to transfer that to the machine. And I continue using or referring to that white paper, and they define machine actionable are those elements in bit sequences that are machine interpretable and belong to a type for which operations have been specified in symbolic grammar. So again, the question is, what does that mean in our context of ontologies and knowledge graphs? And it means that we can link types of elements to certain operations. This could be logical reasoning with using OWL and description logics. It could be also rule-based data transformations such as unit conversion. So the thing with machine actionability is that it is not a Boolean concept. So a data or a datum or metadata is not either or. So it's much more in different degrees of machine actionability. So the more operations have been defined that can read out your data and then do something with it, the more machine actionable it is, of course. And the more open your framework is, the more machine actionable it is, because others can then reuse the data. Other machines could reuse the data. So let's take a look at the actionability of terms and statements. And here we need OWL and description logics. So OWL, we talked about that already. That's the web ontology language. And it provides, and it's a family of languages, and they provide to varying degrees formal semantics that are based on description logic or parts of description logic. So it sounds so difficult because basically we have the different languages within the family of the web ontology languages. They differ in terms of how much description logic they allow. And description logic is a family of logics that are decidable, or mostly decidable, fragments of first-order logic and have attractive and well-understood computational properties. So decidable, what does that mean? Well, in general, you can understand it as if you would have an infinite amount of time, then the reasoner would terminate a certain reasoning activity. They would come to an end with a solution. Of course, we don't have an infinite amount of time, but if it's not decidable, then even an infinite amount of time wouldn't be sufficient. So in other terms, if you use OWL, the chance that a reasoner will come to a conclusion is rather high. If you would use a different framework, first order logic framework, the chance is much, much lesser. So and with the OWL language, certain operators are supported that refer to the different types of resources that we have and distinguish in OWL. So we have the classes, and with the classes you can do the union of classes, the intersection of classes, the complement, which is basically negation, the cardinality, which is when you count things, disjunctionality, and equivalence. You can make statements where you relate two classes through the union operator or the intersection operator and so on. And you can also have operators for the properties, like for instance, transitivity or symmetry. Transitive is the part of relation is transitive, which means if A is part of B and B is part of C, then I can say A must be part of C. Or subclass relations the same. And symmetry means, like in neighborhood, if A is neighbor of B, then B is also neighbor of A. And these operators form the basis for the so-called reasoning. And here we have an example. So if this here is true, we have a certain instance of the class data item that is a specified output of an instance of the class counting. Then the reasoner, given that this here is true, that's background knowledge for the reasoner, then the reasoner can say, then this instance must be also an instance of the class count. Because count is defined as anything that is an data item and that is an output of counting. This is a data item that is an output of counting. So it must be a count instance. Or here we have this X part of Y part of Z. And if we have part of defined as being transitive, then we can conclude, or the reasoner can conclude, that X is part of Z. So this can be understood as knowledge that is implicit in the graph that can be made explicit via reasoning, which is, of course, something that could be very valuable considering you have a large graph of 1 million triples. But again, we have problems here. And one is what I call logical interoperability. Different ontologies can be based on different logical frameworks. We have talked about OWL-based ontologies, which are based on description logics, but there are other ontologies that exist out there that use common logic interchange format, which is based on first-order logic. So here the problem is first-order logic understands description logic, but description logic doesn't understand first-order logic, so you have an interoperability only in one direction, but not in the other one. But this sounds terrible, but the practice is basically that most ontologies, if they are built on a logical framework, it is on description logics, and they use OWL. So there are not many ontologies that are based on first-order logic. Okay, so we know now what's required for the actionability. We need OWL operators and description logic. Now, what does that have to do with the FAIR guiding principles, and what is that? Well, it has been published in 2016, and it's not a standard. It's a set of principles with a goal to basically guide future developments in data management, in the field of data management. And you see here we have these 4 principles: findable, accessible, interoperable, and reusable. And each of them has a certain amount of criteria that help you, like guiding criteria, that help you to end up with FAIR data and metadata. And this is very important. FAIR data and metadata applies to humans and machines. So data must be findable, accessible, interoperable, and reusable easily for humans and machines. And If we take a look at knowledge graphs and ontologies, we see that for the principle of findability, we can use URIs. We can, for the terms, and we can use the schemata, the patterns, for the statements. And then we need, in addition to that, the term mappings and the schema crosswalks. And then we have a certain chance to really find everything that we're looking for. In terms of accessibility, we need some tools that help us then to find the things. So and then access it. So that's Sparkle. That's a query language for for RDF data. But there are other openly available query protocols that can be used for other types of data sets. And then in addition to that, whenever we delete data, we should have at least some metadata still accessible in the graph. Then in terms of interoperability, I talked about that before. So we had this terminological interoperability, schematic, ontological, logical. These all are aspects of interoperability. And OWL-based ontologies and schemata provide us with this type of interoperability if you still consider the problems that I've mentioned before. And then to export data and metadata, you should also be able to export in other formats because you want to have data to be ready and fit for use, which means if I have a certain tool I want to use to analyze my data that expects the data in a certain format, I want to be able to export the data from a database into that format. That would be cool, right? So I have no transformation steps in between. And the more formats we provide, the more fit for use is our data. And the more it is interoperable with certain analysis tools. Then in terms of reuse, data and metadata must be clearly described. So these are more like soft criteria with clear specification of the usage license, with detailed provenance and following community standards. And as I said, ontologies and knowledge graphs provide technological and conceptual solutions for going fair. So for strategies to come up with workflows that result in fair data and metadata. So that's basically it. The summary, we talked about how we communicate as humans, terms, that we need some conventions, we need information, provide the sender and the receiver with the same lexical competence. So we need a term, we need the ontological definition that provides us with meaning, we need recognition criteria that provide us with information for the reference of the term. We need the same for statements. We also need here conventions, grammar and syntax. We need a syntax tree with defined positions and associated semantic roles. And both the sender and the receiver must know these rules to be able to formulate a statement and understand a statement. Then we talked about what are data, and that basically data schemata are the same as syntax trees. Both have their positions with associated semantic roles, and both are important for humans and machines to make sense out of statements. And data are basically statements, just formalized. So we talked about readability for machines in the context of ontologies and knowledge graphs. And for the terms, we need URIs, and then, of course, the literals. And for the statement, we need RDF. In terms of interpretability, for the terms, we need ontologies, and for the statements, graph patterns. And then finally, for the machine actionability of data and metadata, we need the web ontology language, we need operators and description logic. And the more defined operators we have for a certain type of URI, the more machine actionable that specific type of URI becomes. And then we talked about the fairness of data and metadata and how ontologies and knowledge graphs provide technical and conceptual solutions for going fair. And that's it. Thank you.